I'm going to go back to the mode register. Again, I want to emphasize flash memory has a software driver that you have to use to do various operations on the device. This has a software driver to do the initialization of the RAM before you can actually use it for read and write operations. We're going to see that there are a set of commands that are issued to use this particular device. But I want to cover or go back over a couple things on this mode register. We talked a little bit about burst length. We're going to be discussing that in a little more detail in this lecture. Bit 3 determines the burst type, sequential or interleave. In the sequential burst type, if the 3 least significant bits are 111, then the burst is full page. And on the next page, note number 1, it tells you how long, how many memory locations are accessed in a full page burst. If you look at the mode register, and this is not intuitive, where does the data that goes into the mode register come from?
It's from your address lines that you would normally use.
Say again?
The address lines that you would normally use to select your addresses.
Well, what does the diagram show?
The address bus.
The address bus. Normally you would expect a data bus would provide the data. But on this particular device, we do a load memory or load mode register command to a specific address, and the address that you choose, it provides the data that gets stored into the mode register. I have no idea why they do it that way. It is what it is. We also had bits 4, 5, and 6 determine something called column address stroke latency, and your choices were 2 or 3 clocks. So what this does is it's the delay in clock cycles between the registration of a read command and the availability of the first data. If you're doing a single read command or if you're doing a burst mode, it's going to take 2 clock cycles from when you start the read operation by issuing a read command and when you actually see the data on the database. So this shows the example for a CS latency 2 and 3. So right here you issued a read command followed by 2 no-ops. And you'll notice you have 1, 2 clocks, and at the end of the second clock is when you will see data on the database. For CAS latency 3, you have to do a read and 3 no-ops. There's 1 clock, 2 clocks, 3 clocks, and then you see the data. So this just shows you the difference between a CAS latency of 2 and a CAS latency of 3. Okay, so table 6 shows the various commands that you have for this particular device. And the table shows you the format of the commands. The commands are comprised of chip select, row address stroke, column address stroke, write enable, GQM, the data, on the data lines, the address, and then there's notes. Of course, we have that commandment that'll show, read all notes associated with the table. So this command inhibit and command no op, these were the commands that during the initialization procedure, you saw that in certain steps it says you can't issue any command other than a command inhibitor or a no op command. This is the structure of those particular commands. For a command inhibit, the chip select is high, and it doesn't matter what you've got on any other signal. For no op, it's low, but you've got high on column and row address row, and the write enable, and it doesn't matter what you have on anything else. On the read command, remember that the memory is organized in 4 banks, so you have to select a bank and a column within that particular bank. And so these are the respective values for chip select, row address row, column address row, write enable. On the address lines is where you will put the bank and the column that you want. Let's see, what's node 8? I'm sorry. Activates and deactivates the DQs during write and reads. Okay. When you issue a read or write command, if you have selected a burst mode of something other than 1, the burst will start. We'll look at the timing of that shortly. If I'm doing a full page burst, that's a specified number of addresses, but maybe I don't need all of those particular memory locations. So there is a burst terminate command. For example, let's suppose I've got a 4-bit device, so a burst mode read will read 4K worth of locations. Let's suppose I only want to access 2K. What you can do is start the full page access and then terminate it after you've got the 2K of data that's been read in. So you don't have to go through the entire 4K read operation when you only need a portion of the data. Here's your load register command. Chip select the 2 address strobes are low. Write enable is low. On the address line, you put the opcode. That opcode will be the 12-bit value that you want stored in the mode register. Doesn't matter what you have on the data lines. And then it tells you in here what the various bits on the address bus do. Okay, so this shows the timing for a burst read, and it's similar for a burst write, but let me go back for a second to this particular figure. This shows the read of a single memory location. And you can see that it takes 2 clocks, if I have a CAS latency of 2, in order to get the data. So let's suppose that I want to read 8 consecutive memory locations. I could do 8 independent read operations. Each one of them would take, according to this figure right here, 2 clocks. Let's look at the burst read command. This is for a CAS latency of 2. On the first read operation, you have to go through 2 clocks to get the first data out, but then notice that the next data in the burst comes out of the next clock. So you save a clock on every read operation by using the burst mode. And so this timing diagram shows you the advantage of doing bursts. And remember, this is a large memory device in terms of density, how many memory locations there are. And you're typically using this in an application where if I'm doing a read or write, you can do to individual memory locations, but typically what you're doing is getting a block of data out of, or writing a block of data into this particular device. So you can see from this figure 11 the real advantage of being able to do burst mode. You can save quite a bit of clocks. There's the write command. There's the write burst. Any questions on the synchronized DRAM? Hearing none, we're going to go on to the next topic. An acronym I expect you to know. Programmable logic devices. Now, if you were going to go out and buy a laptop, you would have several options available to you. And as you select more options, more features, the price goes up. So for example, the laptop may come in 2 size displays and you choose the larger display. Or you may choose 64 gigabytes of RAM instead of 32 gigabytes of RAM. Or you may choose the higher clock speed. There's different features, and as you add these features, of course, the price goes up. While the same is true on these devices, the more flexibility, the more capability that you want inside the chip, the more you're going to pay for it. So let's take a look at the simplest programmable logic device. And incidentally, these have been around for 35 years, something like that. Our old friend, the PAL 16L, 16R series. Now let me go down here to the 16R6. Okay, so here's the 16R6. It's got 6 registers in it, 2 combinational logic outputs, and the output equations or the excitation equations are determined by you taking a Boolean equation in sum of products form and programming this So you select which inputs feed which AND gates to implement your Boolean equation. Now this architecture is fixed. And what we mean by fixed is you can't really change anything. You can program the inputs to these AND gates, but you can't change the nature of the outputs. Pin 16 is a register output. Can't do anything about that. It may turn out that if you're going to use this type of programmable logic device, the layout of the printed circuit board might be easier if, say, the registers are at the higher pins and the two combinational logic pins, two combinational logic outputs are at pin 12 and 13. But you can't change that. This is a fixed architecture. Let's suppose that I want to implement a more finite state machine, 22 states and 3 outputs. So it has 22 states. How many registers do I need? We're assuming fully encoded. How many? Gonna need 5 flip-flops. Well, this particular device provides me 6, so I've got enough flip-flops. But you'll notice that I need 3 combinational logic outputs, and this device only provides 2. So I couldn't use a 16R6 to implement this finite state machine. If I go to a R4, well, now I have enough combinational logic outputs, but I don't have enough registers to implement the state memory. So I can't use the 16R4. So we can take a look at the 16R8. That certainly gives me enough flip-flops to implement the state memory, but there are no combinational logic outputs. So appears like none of these particular devices in the 16L8, 16R468 will provide me the architecture I need to implement that finite state machine. So let's choose a device. It's going to be more expensive, but it's going to give me more flexibility. And this is an example of one. This is a GAL, generic array logic. This happens to be a 22V10. Oh, incidentally, on the PAL, those PAL devices are OTP, which stands for one-time programmable. So if you made a mistake in the programming, throw the chip away. There's nothing else you can do. Yeah.
Is that because you're blowing fuses to program it, or what's the deal?
I guess you could think of it as blowing fuses, because what you've got is this will be an input to an AND gate, and this is a one of those columns in the AND or array. And this would be hooked to one of the inputs. And so there would be a connection here between this input and here. And when I program it, if I remove that, then that input's no longer connected to the AND gate. So if you want to think of it in terms of fuses, yes, you would program it by removing connections. And as a result of that, you can't reprogram it because there's no way to reform those particular fuses. Okay, this is a gal. We're going to pay more for this, but we're going to get more flexibility. For one thing, these are reprogrammable devices. You can erase them and reprogram them. So that's one nice feature. If I've made a mistake, I can erase the device and program it with the correct design. Now, in here you have this input with these weird buffers that have got complemented and non-complemented outputs. It goes into an AND OR array similar to the PAL. But you notice you have this OLMC on all of the outputs. And that stands for Output Logic Macro Cell. Output logic macro cell. Now the nice thing about these output logic macro cells, and we'll look at the internal architecture in just a moment, I get to define what kind of output I want, whether it's registered or combinational logic. So now if we go back to our example of a finite state machine with 22 states and 3 outputs, I could implement it in this because I could define 5 of those outputs to be registered to implement the state memory. And I've got a number of outputs left over that I can program to be combinational logic outputs for the outputs of my finite state machine. Comes in a DIP or PLCC. Oh, ordering information. Remember that. Now they give you a table, and here they also give you a formula for getting the ordering information. I'm going to come back to this architecture in just a moment. So here are the 4 possible outputs that you get to choose using these output logic macro cells. I can have a registered output, and that output could be active low or active high. Let me very briefly go back to the PALs. If you look at the PALs, the outputs, whether they're combinational or registered, doesn't matter. That's a tri-statable inverted buffer. So on the PALs, you're stuck with an active low output. We'll would you do if I needed an active high output?
You have to use a separate inverter. Or hit your logic.
If it's tri-statable, does that mean that you can change the state of the actual?
No, it's tri-statable, that means it's high impedance, logic, zero logic.
Oh,
Could you just program the max term equation instead? So no, that would work. Never mind.
okay.
Let's say that you want to program that. And then you could do to Morgan's law. Let's call this Y bar. Y A. And that's what you would program. So you have to play games like that if you're stuck with a device that only provides you an active low output and you need an active high output. It's not a big deal, it's just, that's the way you're gonna have to do a workaround. So now if we go to this gal, I get to choose whether the registered outputs are active low or active high, and we'll see how that's done shortly. You can also have combinatorial or combinational logic outputs, and again, you get your choice between active low and active high. Okay, so I have 4 possible options on the output. And I can define each one of those output logic macro cells to be whatever type of output I want. So how do we do that? Well, let's take a look at the architecture. This is the architecture of a output logic macro cell. So you'll notice coming out of the OR gate, you have a path around the register, and it goes into a mux. Now the output of the mux, which goes to the pin, again, that's an inverting tri-state buffer. But look at this combinational logic output. If I choose on the select lines the upper input on this mux, this combinational logic output gets inverted again, it's active high. If, however, I chose the second input on the mux, that would be a combinational logic output. It goes through the inverter and I get an active low combinational output. Now let's look at registered. What's that? Q bar with a bulb.
Yeah.
Choose one. You know, pick a lane. At any rate, you take the Q and the Q bar output, and those become 2 inputs into the select, into the multiplexer. And then choosing what you have on the select lines will determine whether I want a registered active low or a registered active high output. So by choosing programming the correct select lines on this mux, I can choose whether I want a combinational or registered output and whether I want an active high or active low. If I go back to this diagram, you'll see right here, just a minute. this is what the select lines would be programmed on that 4x1 mux. To get the appropriate, output, yeah.
I know you're gonna yell at me, but, is, just to confirm my understanding, registered output basically just means run through D flip-flop, right?
Yeah.
Cool, okay,
D flip-flops are registers.
cool.
That will be the death knell for, in 351, if that's what you're taking, and you are confused about that. Yes,
That's not very helpful. Are the same select lines for 4-to-1 mux used for the 2-to-1 mux, for like one of the lines?
S0 and S1,
Yes.
this is a 4x1 mux, it requires 2 select lines.
Right, but then there's the 2-to-1 mux for the.
Oh, I haven't got to that yet.
Oh, okay.
I'm gonna cover that now. So, this S0 and S1 are with respect to this 4x1 mux. Okay, so these pins that are connected to the output logic macro cell are bidirectional. I can choose to use those as inputs. Now, if I'm going to use this particular pin here as an input, then this needs to be in the high impedance mode. And you'll notice, like in the PALs, there is an AND gate that drives that control on the tri-state buffer. So I could have a small Boolean equation that dictates if that's in the high impedance state or not. So if I put this in the high impedance state, I'm free to be able to use this pin on the chip as an input. And here's a 2-to-1 mux. So you have your choice of using the registered output or an input from the pin going into that special kind of buffer with the complementary outputs. Now, I guess you could do this as well. If I did not apply an input here, and I did activate that, that could give me feedback back into the AND or array. Because then this would be activated and come back in. But if you're going to use that pin to bring in an external signal, then you would have to tri-state that inverting buffer. So then this diagram shows you exactly what happens for active low and active high outputs. So there's that AND OR array. It's a little bit bigger. You recall in the PALs you had 32 columns. Here I've got, looks like 44 columns. So you have a little bit more inputs that you can use for this AND array. 2, 3, 4, 5, 6, 7, 8. There's more AND gates that feed the OR gates, so you can build up a more complex sum of product form Boolean expression than you can in the PAL. There's propagation delays. And just as we saw before, you have certain timing requirements, maximum clock frequency, setup time and hold time for the registers. You have pulse duration requirements, and so forth. missing here? No. We now come to the king of programmable logic devices. Another acronym. I expect you to know. FPGA. This is the reigning champion of programmable logic devices. Now, this is an old document. It's 25 years old. Came out in 1999. And the reason I'm using this is this is a preliminary product specification. It is, however, the best description I have found on the architecture of a basic FPGA and what it looks like. So as far as an introduction, I think this is an excellent document, and that's why I continue to use it. Contemporary FPGAs are far more sophisticated in terms of what resources they give you on the chip. 351, which computer engineers have to take, which incidentally is offered next quarter. Prerequisite is this class. We discuss FPGA programming, prototyping, and these particular devices are programmed using what is known as a hardware description language. The two primary hardware description languages are Verilog and VHDL. We have chosen Verilog. Doesn't matter which one you want to use. So in that class, the first half of the class is learning the Verilog hardware description language. Verilog is a programming language in every sense of the word, like Python or Java or C or anything else, except its design purpose is to describe digital designs. The second half of the class, we talk about prototyping. How do you program the device? How is it used? Its relationship with respect to application-specific integrated circuits and so forth. But in this class, we'll just do this basic architecture. So this Spartan series of field programmable gate arrays, which are made by Xilinx, in this table 1, it shows the various chips that are available in the Spartan series. To give you an idea of how complex they are, I'm not sure what logic cells means, but let's look at this max system gates. In 171, you should have learned that any digital circuit, regardless of how complex, can be made solely out of 2-input NAND gates or 2-input NOR gates. Right? You did learn that. Okay, good. So if I look at this device right here, it says you can implement a design that had the equivalent of 5,000 two-input NAND gates or NOR gates. Well, that's good for relative comparison, but it's actually kind of useless information because I have absolutely no idea of how complex a circuit you can build if you give me 5,000 two-input NAND gates. How many two-input NAND gates are required to make a 54 HC160 counter? I have no idea. So, it's good for relative comparison. Presumably, in an XCS 40, you could build a circuit that's 8 times more complex than an XCS 05 because of the max system gate comparison. There's a thing called a CLB matrix. Another acronym I'm expecting you know. CLB, configurable logic block. So in the XCS05, the configurable logic block matrix has got 10 rows and 10 columns. The intersection of each row and column is a configurable logic block. And for those of you who attended the public school system and never learned how to multiply, they provide this column that tells you that 10 times 10 is 100.
Good to know.
We'll take a look at the configurable logic block shortly. Now, just to put this in perspective, in the Spartan series, and again, this document's 25 years old, the XCS 40, which is the largest device, has got 784 configurable logic blocks. Contemporary FPGAs have got at least an order of magnitude higher, maybe even 2 orders of magnitude, considerably larger devices. No examples in this canvas. So this is the internal architecture, and this is simplified. This shows a 4x4 matrix of configurable logic blocks. The smallest was 10 by 10. Before I get into this, why don't we take a 5-minute break and we'll pick up here after the break.